Dear colleagues, let me present research a lightweight secure boot mechanism for protection the firmware of IoT devices by authors Olena Danchenko, Inna Rozlomii, Andriy Yarmilko, and Sergei Naumenko. Today, IoT devices with limited hardware capabilities are increasingly used in critical applications. Their firmware controls how they function and interact with the environment. But during the initial boot phase, this firmware is vulnerable to attacks. In powerful systems, secure boot protects this stage by verifying software integrity before execution. However, standard security boot solutions are too demanding for low-resource devices. That's why our research focuses on developing a lightweight secure boot mechanism, one that's efficient, secure, and suitable for constrained IoT environments. To provide some context, protection firmware from the very first boot step is critical for building trust in IoT devices. Secure boot verifies the authenticity of firmware before it runs. But traditional versions rely on UEFI, TPM, and other hardware that low-end microcontrollers like STM32 or ESP8266 typically lack. Recent research explores lightweight cryptographic primitives such as Blake2S based hashes or compact digital signatures like ED25519 as more suitable alternatives. Some approaches even omit signatures to reduce computer load through this affects source authentication. Other solutions involve partial boot verification or secure elements, but they often exceeded the capabilities of ultra-low power devices. This highlights the need for a more efficient and scalable secure boot design tailored to constrained IoT platforms. The main purpose of our research is to develop and test a lightweight secure boot mechanism specially designed for IoT devices with limited hardware resources. The idea is to ensure that only trusted firmware runs on the devices, even when they lack powerful processors or built-in cryptographic models. To achieve this, we defined several objectives. First, we implemented a multi-phase verification process that focuses only on critical memory regions. We selected lightweight hash function like Spongent to minimize energy consumption and memory use. We also tested the solution on STM32 and ESP8266 microcontrollers to ensure it works under real hardware constraints. And finally, we added optimal digital signature support using compact ECDSA for use in scenarios that require strong authentication. To build a secure boot mechanism suitable for IoT devices, we first had to rethink the standard security requirements. These devices usually lack dedicated cryptographic models, large memory, or secure key storage, so classical secure boot solutions are simply too heavy. Our approach focused on preserving the key security properties while staying within tight hardware limits. The first requirement is verifying firmware integrity before execution. This is done by comparing a lightweight cryptographic hash using functions like SponGet, Photon, or Blake2S against a reference value. We also had to ensure the bootloader itself is protected. Ideally, it should be stored in ROM or at least verified through a cryptographic link to the main firmware. Finally, memory footprint and startup time are critical. The entire mechanism must fit into very limited flash and RAM and introduce minimal delay at startup, especially important for sensor-based or real-time applications. Figure on slide shows the minimal components needed to achieve this, including hash verification, secure storage, and key reference. The proposed architecture is designed to perform lightweight multi-pass verification before any firmware code is executed. Immediately after power on or reset, the bootloader is launched. It's the only trusted component at this stage. The bootloader reads the reference hash from secure memory and computes a new hash of the actual firmware using a lightweight algorithm like Sponget. If the hash is matched, the system process to load the main firmware. If not, it either enters safe mode or executes a fallback recovery procedure. To reduce overhead, only critical memory regions, such as interrupt vectors or initializer blocks, are verified. Additional components like a random number generator or public key infrastructure are activated only when needed, keeping energy consumption low. This architecture is flexible and scalable. It works on various hardware platforms while maintaining the essential integrity checks. As shown in figure, the structure ensures security without compromising system responsiveness or energy efficiency. In this architecture, the reference hash is stored in protected memory region, either in flash with read-only access or when available in a dedicated ROM segment. This ensures that the hash cannot be modified after deployment. To reduce overhead, the system verifies only critical parts of firmware, such as the interrupt vector table, initialization, routines, or network-related functions, instead of hashing the entire image. This keeps the verification process fast and energy efficient. The bootloader is responsible for computing the hash of these selected regions using a lightweight algorithm and comparing it launched. If not, the device enters a secure fallback state such as safe mode or lockout interface or recovery method require mode. Importantly, intermediate data is not stored in volatile memory during this process, which helps prevent tampering. Some implementations also support multiple valid hashes, allowing fallback to only firmware versions if needed. To evaluate the proposed architecture, we implemented and tested a security boot prototype on two widely used microcontroller platforms, the STM32 and the ESP8266. These platforms were selected due to their popularity in low-power IoT applications and their limited memory and processing power, which makes them ideal for testing lightweight security mechanisms. The prototype includes a 5 kilobyte bootloader, the Sprongket hashing module, and a security storage area for the reference hash. We use a 32 kilobytes firmware image with deliberately modified sections, like the interrupts vector and data processing routines, to simulate temporary scenarios. All code was written in C. For STM32, we used GCC and STM Cube Monitor, and for ESP8266, Arduino Core. Real-time energy and timing measurements were done with a INA219 sensor and an oscilloscope. This setup allowed us to accurately measure the key performance metrics of the mechanism under real hardware constraints. Here you can see the main results of the experimental evolution. On the STM32 platform, the full verification process took just over 21 milliseconds, with Sprongket hashing accounting for majority of that time. On the ESP8266, the full process took about 29 milliseconds. Importantly, energy consumption stayed under 10, 11 microjoules per verification, and RAM overhead was minimal. In both cases, the system successfully detected all tampering attempts. When modified firmware was loaded, the devices either entered safe mode or triggered a rollback procedure without executing the compromised code. Compared to traditional secure boot solutions based on digital signature and elliptic curves, our approach achieved 3 to 4 times faster startup and consumed significantly less energy, which is essentially for battery-powered or time-sensitive systems. These results confirm that the architecture is available for real-world IoT applications, especially where both security and efficiency are required. To summarize, our research confirms that a lightweight security boot mechanism can be effectively implemented on resource-constrained platforms like STM32 and ESP8266 without requiring hardware cryptographic models. By using the spongent hash function and verifying only critical segments of the firmware, we achieved startup times under 30 milliseconds and energy used below 11 microjoules, which is suitable for battery-powered and time-sensitive IoT systems. Importantly, all firmware tampering attempts were successfully detected. This shows the mechanism's potential for security embedded systems at a basic but reliable level. However, some limitations remain. For example, the reference hash is currently stored in plain text, and secure firmware updates are not yet supported. These issues will be addressed in future work. We plan to add hash abstraction, digital signatures, and secure update capabilities, including support for remote trust sources like TPM or secure servers. Our goal is to make this solution a scalable foundation for secure, self-healing IoT environments. Thank you for your attention.